All right, well, I'm going to get started today. Welcome to today's CloudBank Clinic. My name is Anthony Arndt, and I'm a research scientist at the University of Washington's eScience Institute. And I'm here today to talk to you about using Lambda on AWS as a tool for accessing scientific databases. I'm going to anchor this talk in the research work that I've been doing over the last number of years as a cryospheric scientist. And I want to tell you about a NASA-supported mission called SNOWX that has involved multi-year field campaigns to measure snow properties across a variety of different landscapes. So the purpose of this work is to provide ground validation calibration data sets for remote sensing and satellite observations so that we can actually someday acquire really accurate measurements of snow from space, which is quite a difficult task and requires a lot of ground observations to kind of make sure that we're measuring the right thing. So this is a really rich data set that involves point, line, polygon, and gridded data sets, as well as time series data of things like climate variables. So there's quite a lot of variability in the types of data, but it's also very structured. So it really is well suited to a relational database system. Now, what typically happens is researchers go out and collect observations in their field book. And if we're lucky, that'll make its way into a spreadsheet and a CSV file that may get distributed to a federal data center. But these are often distributed as flat files, and the community doesn't get the full use out of the data sets that we've invested so much energy and time in acquiring. So we have come along as sort of data science experts here at the eScience Institute to partner with these snow communities to help them build relational data systems to curate and distribute their data. What you're looking at is an entity relation diagram of the database that we created. We don't need to go into detail on that, but it just shows that we have created this highly structured tabular format that stores both the observations themselves, the core data sets of the variables that we're collecting, and that's linked through these relationships between the tables to other lookup tables, things like who collected the data and what kind of instrument was used and what kind of observations are available across the suite of measurements. We're deploying this on the PostgreSQL database system. We've chosen that because it is a really reliable, free, open source relational system that's been around for a long time. And it has this really nice extension called PostGIS that enables us to do complex spatial querying as well. So we can do complex joins across these various tables and have very reliable transactions to protect our data that we've invested so much in collecting. As is typically done, we've deployed a database system like this on an AWS EC2 instance. And what people will often do is then distribute the credentials to that database out to their community so that people can make queries against the database from their notebook. And this is the configuration that we started with that you'll see here on the left, this diagram of the actual access patterns to the database after we built it. So you can see the end user on the left will be a researcher with their Jupyter notebook. They're issuing some kind of API request to the database, and they'll get back some data. What we have to do in that case is, like I said, distribute those credentials to those end users. And as you probably know, that's not a very good practice to expose your credentials for your database. It's just not a very secure way to do things. So we came in with a new configuration here shown on the right, and it's going to be the topic of our discussion today, which is to say, let's put the database into a private subnet behind an AWS Lambda function. And that Lambda function takes care of those queries and also manages all of the passwords and security aspects. And we still have the end user on the left there who's communicating with this Lambda function through a public subnet via an internet gateway. This is a much cleaner approach. It's passwordless. It doesn't require us distributing credentials, and it's so-called separation of concerns. And it's a very nice way to manage this kind of scientific data distribution application. So what is AWS Lambda? You may have encountered this before. It is a serverless compute on-demand function execution toolkit. So the essential idea is you write a function, you upload it to AWS Lambda, and then you tell it how you want it to be triggered, and it only runs whenever that trigger occurs. So the beauty of this is There's no servers that you need to provision or manage in any way. AWS is handling all the infrastructure. And crucially, you only pay for the compute time that you use, which is typically in the milliseconds. So it's a much more economical way to deploy a function that is only ever going to be used in a sporadic or so-called bursty kind of workflow. So there's an obvious cost advantage here. Lambda is only running when you invoke it, and it's really great for lightweight event-driven tasks. So what are some of the ways that Lambda typically is used? I'll list 3 of them here. The first, this is a very common application, is let's say you have some files that are scheduled to be uploaded to an S3 bucket. Maybe every day you're gathering some satellite observations that get pushed to an S3 bucket. That will be the trigger for a Lambda function that maybe does some additional algorithmic processing on that, and then that gets output to a metadata file for you as a researcher to look at. This is all automated through these Lambda triggers. A second would be a simple notification service. So let's say you're running a big batch compute on a bunch of snow depth data sets. As soon as that's done, that scheduler says, okay, I'm going to just notify Lambda through an SNS call. And Lambda might then do some additional metadata processing and, again, notify the end user that things are ready to be looked at. And then the final application, the third one there, is the one we'll talk about today. It's a really common and ideal use case for Lambda where there's an API gateway. So a user makes an API request, in our case, some kind of data query. Lambda then is triggered to execute that and route it and handle it through the code that we've written to the database. It issues a SQL query, returns some data as JSON, and gets routed back through an API push back to the user. So that's the one we'll be talking about today. So let me show you just a little bit of this to begin with. So first of all, I'm showing here the open source package that we've called SnowXSQL, and this is a database package that our team has put together. It's sort of an API and a front end to the database, and we'll be coming back to this later. But just to show you where all this lives, this is a very typical way where scientists will gather together sort of the data access patterns, publish it as their own Python package. And so this is something that we distribute out to the community. But the key thing is here, we'll be talking today about how this client accesses the data in a serverless fashion. Okay, so now I'm going to go over to the AWS console. And if you've got your CloudBank credits and you're running AWS, you'll see something similar to this. This is actually my own separate account, but you'll see a very similar interface. And I'm going over to Lambda. I've got a couple of Lambda functions already running from some other work. But just to show you the interface and how this typically looks. So I'm going in to create a Lambda function. And I want you to notice here the different ways that you can choose to create that function. We'll do this one here, and this is the most typical, to author the function from scratch. But I want you to also notice this container image on the right, which we'll be coming back to a little bit later. So let's just do a quick demo function here. And you can see the runtime supported a variety of different languages. We're going to choose Python 3.14 and then simply create the function. So this will spin for just a couple of moments as it creates a Lambda function. And then we'll see another interface for actually editing the function, for monitoring the kinds of requests that it's getting, and so on. So here's the Lambda function interface. It's going to be showing us the code blocks in just a second. This is kind of a Visual Studio style code interface. It pre-populates it with a typical hello world function just to test things out. Okay, so that's what we're going to do, just to show you what a run actually looks like here. Is we go to the test tab, and it's going to give us the opportunity now to just run that function, that simple hello world function. Okay, it already did, and returns some JSON according to the contents of that function. So a very simple example. Over here, as I mentioned, you can do monitoring. There won't be anything in these charts because we've just created the function, but it allows me to monitor, for example, how many of my colleagues are making Lambda requests to our database when we actually set that up here. Okay, so a couple of key things from that quick demo is we have to note that oh, I want to show you one last thing actually in this code section here, is you can actually, write the code directly into here, or what's commonly done is you write some code locally and then you upload it as a zip file. So we'll be referring to this as kind of the zip file approach to working with Lambda functions. But a key thing to remember here is this approach has a 50 megabyte deployment package size limit for zip files. If you've worked in Python, you probably quickly realize that's quite limiting. Okay, so now let's talk about that with respect to the SnowX project that I've been talking about until now. Our SnowX SQL code base that I showed you earlier obviously depends on some of these more these larger Python libraries like NumPy, Pandas, and we need all these geospatial toolkits like GeoAlchemy 2, which quickly exceeds that 50 megabyte limit for the zip file. So when I first set this up, I tried to use zip files, but it was my data and my code base was too large. So I had to think about a different approach. And luckily, Lambda offers us a different way to do this, which is to use what's called a container image. With a container image, that ceiling raises to 10 gigabytes. So we have considerably more space to work with where we can handle these larger packages. Okay, so working with a container is great from that perspective, but it does introduce some additional complexity, which we'll have to talk through here to see how this is configured. But the basic idea is we're going to need to build a container locally using Docker. And so this is sort of containerizing, puts everything into an image that allows me to share that with other people without having to worry a lot about environments, and everything gets packaged and distributed into a self-contained image that is usable across different platforms. So we're going to build that locally. We'll then push it up to Amazon Web Services into what's called the Elastic Container Registry. So it's kind of a catalog of these different images for Lambda to reference, and Lambda will be pointed to one of these ECR images and we'll invoke it upon the trigger that we tell it to use. All right, so we're going to need to build that container image before we push it up to ECR. But what's going to go into that image? Well, we're going to need 4 different things that I'll talk through in the next slides. The first thing is going to be a new Python script that we're going to call the handler. And that's going to route all of the requests and sort of make sure everything gets to where it needs to go with respect to talking to the database. We'll need the Docker file itself. We'll need the requirements of the specific libraries that go into that image, and then the actual code base that we already have written from a long time ago. All right, let's step through each of those in sequence here. The handler function, this is not the entire Python that we've written, but it's just a stripped down version of it. And it contains 4 key elements. So it's a function written in Python where an event is coming in, and the event is going to represent the actual query itself that the user in their notebook is issuing that needs to get routed through to the database. The context, don't worry too much about that. That's just a little bit of information about the metadata of the query, how long it's been running, and so on. So this is the sort of really powerful piece of all this here, the secrets manager. We will have previously uploaded the username and password for the database to a separate service on AWS called Secrets Manager. And then in the code, we have a function that grabs the secrets, puts them into the environment, and allows us to then write a temporary credentials file in this next step. Those credentials are input to a database function call, and that function will gather the username and password and instantiate an engine and a session object. So anyone who's worked with Postgres or other databases in Python, you'll be familiar with the way you start talking to a database is you instantiate a session with that and also an engine that connects you to the database. And the last step here is that event itself gets, we get the actions associated with it. So that'll be like, what kind of data is being requested and what does the user want to look at right now? That gets routed through this handler into the appropriate parts of our code base and also gets serialized correctly, and the return coming out of the database, it will be routed as JSON back to the user. Okay, so that's the first part of what goes into our container. The second is the Docker file itself. And this is, you can think of that as like a cookbook, a recipe for what the Docker image should contain. It's going to need to contain a base Python image, and that's easily acquired because AWS provides these base images with the runtime that are pre-configured. So we start with that base image. We add to it our additional requirements, these additional libraries that we need for our code base in a requirements file. And the third thing we do is we actually copy the entire SnowX code base that I showed you, which also contains that handler file that I showed a couple of slides ago. And the last thing is we tell Lambda which function it needs to invoke. It's that handler Python file that we just talked about. Okay, so that's the contents of the Docker file. Once that's all ready to go, we are ready to build the file itself. So these are just the command line steps that we issue. We build the image, we put a tag on it for that elastic compute registry, so Lambda knows how to identify it and which one is the latest to be run. And then once we're ready, we push it over to AWS into that secure private subnet. All of the code, the handler, is all now over on AWS, and this takes a few minutes to do. Okay, so we've got everything on AWS in the secure location. But now how do we talk to it from the public internet, from the outside world? We're going to do that through what's called a function URL. In the Lambda console, there's a configuration tab that allows you to set up a function URL, and you set the auth type to none, and you get an arbitrary URL, HTTPS endpoint. And in our case, we made this public because you can go grab these flat files off the NASA servers anyhow. There's nothing that we need to secure here. It's openly licensed, so we're making this public to the world. Keep in mind, if you do have sensitive data, you can turn on some other security features, such as using an API key or have the requirement to use AWS account credentials. And then just to emphasize again, that security now all lives on the Lambda side. The users of the Snow community are never going to have to see the database passwords, and all the permissions are handled between Lambda and the actual database. Okay, here's another way to kind of visualize all the complexity that I just stepped through. On the top half of the slide is the user, the client, the scientist who's coming in to work with the data in the public internet. They are working on a Jupyter notebook. And on the bottom half of the slide is all the stuff we just talked about that we pushed into the secure Lambda container on AWS. The handler, the actual API in the SnowX code, and then the database itself, of course, lives there. The way we're talking between those two worlds is what I just mentioned, that function URL through which these HTTPS post requests can conduit through. Okay, so we're going to show you next a demo of how this notebook now goes and gathers some data from the database. I haven't mentioned this yet and shown you the code, but there's a last piece of Python code that we're calling the client. And this is the tool that serializes all the requests on the user side into JSON so they can route through into AWS and gather the data and come back out again. Okay, I think this is easiest to show in a little bit of a demo here. This is a Jupyter notebook explaining the usage of our database. We're going to import some of the libraries we need to make some plots, but the most important import here is the client that I just mentioned itself. So in practice, a user who wants to work with this database, they'll still need to clone our repository, but they're really just needing that Python thin client that is a wrapper around all of this tooling and then routes the requests that are being made in the notebook through to Lambda, and then it coordinates receiving those back to the user. Okay, I'll show how that works in practice. What we do is we instantiate that client in this cell here, and then we get the different kinds of classes. At the beginning of the talk, I told you there's point and layer data, this sort of rich different types of data sets in the data that we're curating here. So I'm going to run this cell. And what this is doing it's creating a connection to the database. And it's just confirming here that this is true. So we've now set up a connection to a Postgres database. Those credentials were passed through, and we didn't have to touch any of that. You'll notice that took a couple of seconds. We'll talk about that cold start thing here in just a moment as part of one of the issues with Lambda. All right, so I'm going to just work with a few of the methods on these layer and point measurement types. And here I'm just saying, what are all the types of data stored in the database? There's snow density, grain size, hardness, things like that. For point measurements, there's the snow depth and density. And we can just query all the different instruments that are being used as well. I'll just do a couple of quick plots. This is the most general one that is going to be a standard way people actually work with gathering data from the database. Typically, somebody will want to put in a bounding box and say, what are all the measurements within a bounding area that I'm studying right now? So we use the from area method on the layer measurements, and we're giving it a bounding box with these coordinates. We can also put some time constraints on it. I want to look at snow temperature in this case, and I'm going to limit my query to 600 just so I don't fill up the data frame too large. Here's the first 5 records. We've made a query against the database, and we have some snow. Oh, that should say temperature. Oh, no, that's the depth of the snowpack, because this is layer data. It's done across different layers. It happens to be 0 degrees temperature in this little example here. Going to do a quick plot to show you what this looks like spatially. I'm plotting all the data that it just returned. This is the Boise Basin in Idaho. Those blue dots are all the snow depth, snow temperature measurements we just queried. And the final plot I want to show you here. I'm not going through this in great detail, but just to show that very quickly, you can create a plot here of snow temperature on the x-axis with depth into the snowpack of several hundred observations. You see how quickly we were able to do that. Typically, snow temperatures getting colder with depth at this time of year, up to 0 degrees at the surface. Quick example of what's possible with this. It's a very powerful tool, and you can see how we can now start integrating data sets across different campaigns throughout the years and relate that to your remote sensing data sets. Okay, so that was my demo. I'm going to just speak to some of the core limitations of Lambda before we wrap up. The first one is there is a 15-minute execution limit on whatever functions you upload. So Lambda will kill your function after 15 minutes. So clearly this is not a great tool for batch compute, for big HPC jobs, or long-running simulations. The second limitation is the cold start latency. The first invocation can take a few seconds to spin up. You saw that today, actually. Not an issue for that kind of work we're doing. But if you have some application where those milliseconds really matter, this would be not a good tool for you. And then we've already talked about the package size constraints. I even still ran into some limitations with the 50 gigabyte limit because of, or 10, that is, because of the just the large size of some of the geospatial libraries like GDAL, if you've worked with that. So you still have to be thoughtful about how you make good use of the space that you have. Serverless, remember, doesn't just mean you can run any analysis without thinking about the infrastructure. You have to still be thoughtful in how you design things. But clearly, Lambda is filling a really interesting niche here. I'll just make a quick point that the helper methods that you saw in the demo that I just did, this is kind of a standard API that we set up for the typical kinds of ways people interface with our data. Well, maybe you want to do more complex joins or multiple table queries or some group by aggregations. Just to note that you have so much flexibility here. If you have a user who's familiar with writing pure SQL, they can write these more complex queries and issue them to the client as a pure SQL query and get this full complexity leveraged, even if it's not something that we're covering in the standard helper methods. This I'm going to leave for you to look at later. I'm not going to go into a lot of detail, but I started to think about what are the other patterns that this kind of architecture enables. Everything from genomics to more of the things in my field in hydrology, remote sensing, where you have stacks of even gridded data, and then that Postgres database acts as a catalog in front of those data sets. I know that's a big issue in genomics when you have these variant self call format files, these VCF files. And you may have a stack of those on S3, but you could use a similar infrastructure to what we've described today to create a really streamlined workflow using Lambda when somebody comes in with a request that sort of subsets that through the metadata catalog that lives in your Postgres database. So I won't go into much more detail there, but I'm happy to brainstorm what sort of other applications can be used here. I'm bringing this all back to CloudBank as we wrap up. There are a number of considerations just to keep in mind if you want to deploy something similar on your own CloudBank account. A big part of the complexity in some of the things that I showed you today are around permissions, making sure that everything that lives in that private subnet is secured from the public access, things like that. And so some of that permission setting through IAM, you would need to maybe coordinate with your CloudBank point of contact to just set up the required roles. In terms of costs, we've already talked about how Lambda is very efficient. It's a pay per invocation. It's a fractions of cents per query. The ECR is also quite cheap. That container registry is not a big consideration. EC2 will be your biggest cost in what I've showed you today, and that's just going to depend on your database size. You'll need a larger EC2 instance and some storage attached to it, depending on how large of the data sets that you're looking at. And you can, of course, we recommend everyone use the Cost Explorer to monitor things. For the configuration I showed, I can't remember, we have multiple gigabytes of data in our Snow database. I think I'm paying somewhere around $200 per month for everything that we're running, or a little bit less. But I'm happy to work with folks to help them learn what's a good usage of their credits. A couple things, again, to watch out for: making sure everything's in the same region, configuring your security groups, and the image architecture should match the Lambda configuration. So some of the deeper details on just making sure all this works in a seamless way. I'm going to finish there and provide links to our code base and some of the AWS tools, the CloudBank resources, and appreciate your attention. I'm happy to answer any questions that you may have.